So as we attempt to look at the electric field and how it goes through the surface, the electric field strength is one quantity that determines how much flux we're capturing through our surface. You have to imagine that our surface is capturing this flux. Of course, there's also the measurement of how concentrated the electric field is on the surface. More field lines would suggest it's more concentrated. So the size of the surface matters. The area of that surface matters. But here's the part that's a little bit trickier. If my surface was turned so that instead of it being perpendicular to those field lines, my surface was turned in such a way that it was aligned with the field lines. So if I turned the piece of paper like, 90 degrees this way, all of a sudden, the field hasn't changed. But now, none of the field lines are actually piercing the area that I have. So the area is the same size, and the field lines are the same, and the concentration's the same. But in this case, there would be no actual flux captured by the surface. In order for there to be a calculatable flux, the field lines have to pierce the surface, either traveling out of the surface or into the surface, which requires that we have a mathematical way to figure out the angle of the surface relative to the angle of the angle of the field. Now, mathematicians and physicists have had to come to agreement on how we measure the direction of a surface. This is probably not something you've ever heard about before, but we have come up with an arrangement to give area a direction. And the direction of an area is perpendicular to its surface. I'll say that again because you're going to want to write that down and put a box around it. The direction of an area is perpendicular to its surface. Pointing away from the enclosed volume. So I'll say that one more time, just so you have it in your notes. But the direction of an area is perpendicular to the surface, pointing away from the enclosed volume. There's no beeping. So if I was to draw in little arrows to indicate the direction of the surface, each one of these arrows represents a small amount of area, and they're pointing in the direction in which I believe they face. That okay so far? Yes, sir. In this case, it wouldn't. I'm just being consistent with the direction I drew that I was twisting my area. But with a flat surface like this that encloses no volume, the direction's arbitrary for what you would call the direction of the surface. Generally, though, if it was back here, it should be pretty clear that I get maximum flux when the electric field is aligned directly with the area. In this case, the angle is 0 degrees. Cosine's a maximum at 0. And there is no flux when the electric field and the direction of the surface are perpendicular, because I have no flux lines piercing my area. In this case, theta would be 90 degrees, and the cosine of 90 degrees is 0. This is how the calculation of flux is intended to work. And this is why we have chosen the direction of the area to be like this. Any questions yet? All right, I'm going to draw a picture, figure out what, and it's going to take me a few seconds, so do what you need to do for the time being. But I want to kind of draw a kind of a generic picture of some non-uniform electric field and a Gaussian surface. All right, so here's my picture. I have some three-dimensional surface, something non-uniform, drawn in space, and there's an electric field in that space. Now, the way Gauss's law is designed to work is it says that the enclosed charge is equal to a constant times the total electric flux. This is what Gauss's law states. Now, the Gaussian surface is a construct. It's not a real surface. I spelled construct wrong, so I'm really excited about that. It's a construct. We create the Gaussian surface that we wish to use in order to use Gauss's law. There are no Gaussian surfaces, and there's not an actual shape like some, plastic bag floating through space. That's not what this is about. The focus on Gauss's law is either to determine how much charge may exist in some volume, or it's to be able to calculate the electric field. That's the purpose of Gauss's law. I'll state that again. Gauss is a law. It's an invariant feature of the universe. We don't understand why it works the way it does, but it is a part of the universe. What you need to understand is that we use Gauss's law for another purpose, not for its intended design, but we use it to determine how much charge might be in a space or to determine what an electric field might be in a space. So we use it. The fact that it's a law just helps us, meaning we know that all of the charge creates a certain amount of electric field. And if we can measure all that electric field, we can tell you how much charge was there. That's what the flux is doing. It's measuring how much total electric field exists coming from our charge. So when we consider an area of space, a region of space, our job is to figure out a Gaussian surface that would help us kind of look at all of the possible electric field that both enters and leaves my volume. And if I can find a way to add it all up, I can use that to determine the charge or determine the electric field. You'll notice in this example, the flux is probably zero. If you don't see why, notice that there's about as many flux lines entering the surface as there are exiting the surface. Do you guys notice that? Also, I've drawn no charges inside that volume, which means the enclosed charge is zero, which would also signal that there's no flux. Now you have to be careful here. Zero flux doesn't mean zero electric field. If I were you, I'd write that down and put an exclamation point there. Zero flux doesn't mean zero electric field. It means that there's an equal amount of flux going into your surface as exiting your surface. But it doesn't tell me what the electric field is. All right. We're going to use Gauss's law to find out the electric field for a test case, for you to see how to use Gauss's law. And just so you guys know, Gauss's law is all about symmetry. The only way to use it is by exploiting the symmetry of your problem. So here's our first example, and it's going to be ridiculous because we know the answer. I have a single point charge in space, and it has a charge of Q. I'd like to figure out the electric field some distance away from Q. All right? Now, the way Gauss's law works is relatively simple. There's about 3 steps to it. The first step is to consider some 3-dimensional shape that you could wrap around your charge distribution. You create the Gaussian surface that best fits your problem. There's some properties you should look for. Like this would be the absolute worst Gaussian surface to use. And the reason is because we already know something about a point charge in space. We expect a point charge in space to have a uniform, spreading out electric field. Something that starts from the center and expands outwards in all directions. If I was just to consider these 4 field lines, I would already notice that the surface I've chosen is probably the wrong surface to use. If we look at each of these places where the field line leaves the surface, we'll notice that they all leave at a different angle. They're all different distances away from the charge, which means they're all going to be different size electric fields. This is probably the worst choice of a surface to use. It doesn't exploit the symmetry of the problem in a way that's useful to us. So then we want to start thinking about maybe a more uniform surface, one that might have more uniform characteristics. So, just to be obtuse, how about, I don't know, a square? I mean, that'd be the absolute worst to use, wouldn't it? I mean, a square is nice in that it's, again, at least a regular figure to which we know how to calculate its area. But again, our big problem comes from having to look at the electric field. You know, the electric field for this line is a different distance away than, say, an electric field from this line to the surface. There's no symmetry here. Every field line is going to pierce that surface at a different angle, and it's going to be a different distance away. Hey, for you to miss those tweets. When we consider surfaces that might work or might work better, we're trying to find something that uses the symmetry of the problem. And I think many of you probably realize that one of the better surfaces to use would probably be a sphere. And to place that sphere in such a way that it is concentric with the charge. The nice thing about using a sphere is that a sphere will have points that are all the same distance away from the charge, meaning the radius of the sphere could be set up in such a way that every single part of this area is the same distance away from my point charge. And something else kind of important here, if I do use a sphere, no matter which field line I look at, by definition, any line that comes from the center of a sphere to its surface is going to strike the sphere at a 90-degree angle, which means that the direction of the area here will be right along the direction of the electric field. So I am choosing a surface that exploits the symmetry of the electric field of a point charge. In fact, right now, I think we could consider writing out what this must look like. E dot dA. And they're vectors. So we're going to consider one place where an electric field line leaves the surface. And then we'll add up all of them. So if I consider this one place, I know I have a piece of surface that has an angle of 0 degrees with the electric field. Now, I don't know the size of the electric field there. I do know that I can probably rewrite this for that one location. Now, I have to add up every location, so let's consider all the locations that could possibly exist. When I look at this location, will the direction of the area be in the same direction as the electric field? When I consider this location, will the direction of the area be in the same direction as the electric field? Can you imagine a spot anywhere around here where that wouldn't be true? So that suggests that every single possible location where the electric field leaves the area is going to have an angle of 0 degrees. Next, the size of the electric field. We know from prior work here that the electric field is based on how far away you are. Would you agree that we are always the same distance away from the charge at every spot on the circle? That means that our electric field is probably the same size everywhere, which makes it a constant. And again, this will almost always be our goal, to come up with a way for the electric field to be a constant along our surface. That's exploiting the symmetry. If that's a constant, that means that the electric field and the angle get to come outside of the integral. And all that's left for me to do is add up the total area of the surface. This is how we will use Gauss's law. Every single example that will come up, we are going to attempt to make the electric field some kind of constant. We're going to try and take it out of our function and be left with just some function that requires us to add up the area. And the best part about this is I don't have to do any calculus. The true goal of Gauss's law is to not do calculus, is to try and find a way that we already know the answer to what the sum is. For example, do you know the area of a sphere? You guys don't remember the surface area of a sphere? Oh, that's so disappointing. But it's okay, because if you didn't remember, it would actually be on the equation sheet. They give the basic shapes and their geometries. The area of a sphere is 4 pi r squared. Volume 4/3 pi r cubed. All areas are going to have a part that's squared. All volumes are going to have a part that's cubed. So keep in mind, memorizing that will help you, but it's not all that big a deal. So let's put this back together. Our flux is going to be E times cosine of theta, cosine of 0 times 4 pi capital R squared, because I used capital R as the radius of the sphere. This is the flux of a point charge inside a sphere. Now, just a reminder, to make this Gauss's law, we multiply by a constant. And this constant is This constant is called the permittivity constant. We're going to get to that in just a minute. But hold on a second. There we go. So Q enclosed equals the permittivity constant times the total flux. For what we've just put together, that's capital Q, the charge enclosed, permittivity constant times 4 pi r squared times E. Cosine of 0 is 1. Now, I said to you before that the goal here is to use this to either figure out how much charge is enclosed or to figure out what the electric field is. This actually could be used to give me an expression for the electric field around a point charge. An expression we already know. Right, this isn't a surprise. This is the electric field that we would have gotten from Coulomb's law. The issue is Coulomb didn't know anything about Gauss's law. Gauss's law, though, proves Coulomb's law to be true, except that Coulomb's law had Coulomb's constant. And we have this collection of constants here. Now, just so you guys know, Coulomb's constant's not a true constant. Coulomb's constant is now known to be this collection of constants. And just to make sure that you kind of see that, I'd like you to figure out what this value would be using the accepted values for 4, pi, and epsilon naught. Just so you guys know, epsilon naught, the permittivity constant, is 8.85 times 10 to the negative 12. And the unit is Coulomb squared per Newton meter squared. So I'd like you to take a few minutes and figure out what that is. Meaning Coulomb's constant all along has actually been based on this constant. Now, you might be asking, what's the big deal? Why would I care? Why didn't I just do this from the beginning? There are reasons, and I want to spend a few minutes just for your notes. The permittivity constant is considered a universal constant. We believe that the permittivity constant is the same everywhere in the universe. Coulomb's constant is named for the person Coulomb because that's what he did in his experiments. Permittivity represents how easily an electric field gets established in a vacuum. That's its meaning. It's how the universe works. There are very few natural constants like this, but it's about how an electric field gets established in a vacuum. We will talk a lot about permittivity throughout the year because it's measurable apart from Coulomb's law. So that's the base. Let's say that my surface was arced like this. I mean, still, there really is no enclosed volume. So it would be an arbitrary choice to decide whether you would draw your area this way or draw it internal. Draw it on the concave side instead of the convex side. Now, for you guys who don't follow all of this, please pay very close attention. I said my words and chose my words very carefully. And that's on purpose because I want you to understand something here. The area is perpendicular to the surface. That's been specifically chosen in such a way that if the surface isn't flat, the area is still perpendicular to a tangent line of that surface. So these arrows are designed to be perpendicular to a tangent line that was drawn at that point. Does that make sense? So the direction of your area can be changing all the time if the surface in which the flux is piercing is not uniform. Now, this sounds a lot more complicated than it will be in practice. I just want you to understand that. But you have to have an understanding of what flux means, because there's going to be conceptual questions about flux, and there's going to be operational questions about flux, and you need to be prepared for both. So I want to talk to you about a couple of instances of flux, but I want to remind you of something bigger and more broad. When we go back to the original formula for flux, it's the dot product between the direction of the electric field and the direction of the area. The dot product, if you don't remember this from your prior physics class, is the product of each vector, their magnitude, times the cosine of the angle between them. Times the cosine of the angle between them. We did do this last year. It was work. Work was based on the dot product between force and displacement. That's why the cosine shows up. If you don't remember the definition of work, it's anytime a force is used to move an object, that force has to be in the direction of the displacement. The dot product measures how much of the force is directed along the displacement vector. We use the same kind of product for flux.